Hello, everyone.
Thank you.
Hello, Brett.
Hello.
Hey guys.
Yeah, because they're using 5 volts.
Hello, Brian.
I don't think there's power.
Hello. Give me a second to get settled.
Yeah, we'll do. We'll start when you're ready.
So, Brian, I wanted to introduce myself. I'm Brett Bachman, live in Santa Fe, New Mexico. I've been working with these guys closely for months, and
Yeah.
I'm very proud of what they've done. So I hope you'll like it. I think it looks great.
That's awesome. Yeah, glad to meet you. Yeah, I'm excited to see the final product too. We've had multiple rounds of email
We have.
conversations, and
hmm
this is a culmination of at least what, 6, 7, 8 months worth of work.
Yeah,
So,
for us, we started back in July, so 10 months almost. Yeah,
yep,
big moment.
awesome. All right, so I'm pretty much ready when you guys are. Did you guys start the recording?
Yep.
Okay, awesome. Do you have anything that you want to present? A couple teams, some of my teams, you guys are my last team. So some of my teams have presented like a presentation up front.
Yeah.
Others have just gone right into the checklist.
So we have a PowerPoint.
Okay.
We'll also follow whatever checklist you have as well, pulled up. And then we have the rocket on the table. We have the electronics on the table as well. So if there's anything you want to inspect a little bit closer, we can also do that.
Yep. We'll take a look at everything, but we can start with your presentation.
Cool. And then if there's anything that we miss afterwards on your checklist, just let me know. We can hit those things.
I got it right here, so we're set.
Beautiful. Cool. Let me pull it up and share my screen.
Okay.
Brett, could you enable screen sharing? Yay. Right. Can you get thumbs up? Everyone can see it? Beautiful. All right. Let me move my screen sharing bar a little bit out of the way so I can see the text. Yeah. So moving right into it. Let me hide this as well. There we go. So probably already familiar with this, Brian, but we're competing in the 30K COTS category. Our rocket this year is named Escalante. We've been sure to extensively ground test this rocket with its telemetry systems. We've tested GPS. We've ground tested the CO2 system as well on multiple occasions. And we've also launched smaller L2 rockets to demonstrate that we can perform CO2 and single bay deployments safely. Unfortunately, we weren't able to do a test launch of our rocket this year due to weather issues in local launches nearby. So they were all canceled and we weren't able to get a proper test flight in this year.
It happens.
Yep. So a little bit of a rocket. Here's a first picture of it. This is Escalante. Just got it vinyl wrapped the other day. We're really proud of how it looks.
Looks good.
Yeah. So we have a 6-inch airframe. We have 3 fins. Each fin has a semi-span of 6.4 inches, which gives it a fin caliber of a little bit over 1. It's like 1.08, something along those lines. The tip cord is 2.2 inches. The root cord is 12 inches. The total vehicle length is 119. Vehicle weight is 32. Propellant weight, since we're using an O5500, is 21.6. Our full takeoff weight will be 76.5 pounds, give or take. That's what we're predicting.
Pretty good.
Yeah, we're happy with that. Some basic simulation stats for you. Our minimal static margin during flight is 1.63 caliber. We currently in Open Rocket have a projected apogee of 31,211 feet. We plan to bring that down with weights, and then depending on wind and other weather conditions, that's obviously expected to fluctuate. Our velocity off the rod is 138 feet per second, with a max velocity of just over 2,000 feet per second, or about around Mach 1.8. Our deployment velocity of the drogue is about 95 feet per second, at apogee according to Open Rocket, and we have a ground hit velocity of around 21 feet per second. The thrust weight ratio of the rocket at peak thrust is 16:1, with a maximum acceleration at that point of 24.4 Gs. Motor configuration is an O5500X-PS. Our center of pressure and center of gravity are separated by about 10 inches, and this is from the nose cone tip. Any questions based on this graph or anything else?
Have you looked at your altitude with other types of simulations?
Yes. So,
Open Rocket, I don't think does really good supersonic. The last time I checked, it does supersonic estimates.
yeah.
Can I
Tyson.
talk about that for a moment?
Yeah. Go for it, Tyson.
Okay, so I have run all of our simulations. I've done testing with RAS Arrow, Rocket Pi, and Open Rocket, and doing my own simulation listeners, etc., and Monte Carlo simulations on all of them. We have this agreement of apogee between the three systems of about 100 feet difference between the different three. And so we're pretty solid about this number that we're presenting here from Open Rocket, but we have that verification from all the other systems as well.
Okay. I'm surprised you're getting that level of agreement between Open Rocket and RAS Arrow, but if you are, you are.
Yeah, so we've rewritten a bunch of stuff that is in Open Rocket to actually use higher fidelity supersonic simulation modeling. So it doesn't use the base Open Rocket.
That explains it. Okay, very good.
Yep. And then just to put the final nail in the coffin, we've done high fidelity CFD simulation modeling. We've exported the drag coefficients from those CFD models and put it into Rocket Pi to do our flight trajectory analysis. And we get pretty close with that as well.
Very good.
Yep. Moving on to the next slide then. Flight narrative. Here's a nice little graphic one of our GNC guys put together just to give you an idea. We plan for our boost. That's a 4-second burn for this motor. That's going to be between 0 feet and about 5,000 feet above ground level. Coasting will take about, that should say T plus 0.0.
I noticed that.
Whatever.
4/100ths of a second. That's a hell of a burn.
Oh well, you get the idea. 41 seconds into flight is how long we expect coasting to take, and then apogee at around 41 seconds. Drogue chute deployment for 42 seconds into flight, and we expect our rocket to be descending for about 4 minutes 20 seconds, give or take, underneath the drogue before we hit 1,500 feet above ground level. From there, we plan to deploy the main chute and then do touchdown. Just for net reference again, the main descent rate is 21 feet per second, and the drogue descent rate is 95 feet per second.
All right.
Cool. Haley, for our construction narrative, we'll turn it over to her.
Okay, there we go. Awesome. So our rocket airframe is entirely made out of carbon fiber that we manufactured in-house. We have pre-preg that was donated to us by, I think, Firefly is the one that we're using. All of that was then cured according to datasheet recommendations, and we have done like compression testing on our tubes to make sure that they withstand the force needed. I believe we have safety factor about 10 before delamination. So we should be totally fine in terms of airframe strength. In order to then manufacture or to finish the tube so that they're the right, I guess, surface finish that we want and size that we want, is we'll wet sand. We wet sanded all of our tubes to about 400, 800 grit, and then cut it to the size needed. Oh, sorry, what?
1,000, but not much of it.
1,000. Sorry, I forgot where the paper ends and where the little things start. We went to the paper. Wet sanded to about 1,000 grit, cut to size, made sure that all of our edges were level, and then we're vinyl wrapping our carbon fiber. In previous years, we epoxy coated and then polished that. However, that was the main weight of our rocket, and we were trying to save weight, and so we went to vinyl wrapping instead to get that final finish. The body tubes are attached to couplers via bolts. These are M4 bolts, which have a safety factor calculated of above 4, looking at shear of the bolt, and they are screwed into either plywood bulkheads or brass inserts to ensure that they are actually threaded in, held in, and we are getting a little bit of preloading to make sure that those bolts don't fall out with any sort of vibrations. The inner tube that holds the motor is attached to the body via screws and epoxy holding in our centering ring so that we don't have any concern there. And then all of the force transfer from that motor is with a thrust plate. So we're not actually concerned about thrust being transferred via those centering rings. Still though, they are attached with epoxy and bolts. And then our rail buttons are aluminum custom machined, and those are held on with bolts as well. Nose cone is a commercial filament wound nose cone. Ogive, commercially made aluminum tip for that. And then the tail cone we 3D printed and then layered with epoxy so that we shouldn't have concerns with weakness along the layers in that 3D print. And then, like I said, we have plywood, bulkheads, and centering rings. Those are all laser cut with 1/2-inch plywood. And then where we're concerned with tear through for bolts, particularly with the payload sitting on one of the bulkheads, and then our parachute attachment points, we do have layers of carbon fiber sheets so that we have those carbon fibers resisting any U-bolt pull through. I believe that's
Very
all
good.
for. Any questions there?
Nope. That looks
Okay,
great.
perfect. Next slide, Barry. Okay, awesome. One concern that we had, you know that we do good testing when we can say that we found problems with testing. So we know that our ground testing was good because it didn't work the first time. Because we're using CO2 injection, we have to be really concerned about the seal that we're getting with our couplers. However, we also want to make sure that our couplers are not too tight so that they don't actually, that the CO2 injection doesn't actually work. And so we use Kaplan tape to make sure that we have a really good fit between our coupler and our outer body tube, so that we don't get any sort of vertical wiggle in the rocket while it's on the launch trail, which would affect our flight path. And then, but also the surface finish of the tape, and also just its more heat resistant properties, make sure that we don't get any sticking between the tape and the outer airframe. Additionally, we had holes that are naturally just have to happen because of the way our AV bay was constructed. And we're using Loctite blue tacky tape, which is our more official version of Play-Doh, in order to make sure that we don't have any air leakage through those holes that the wires come through. And finally, we have an O-ring that's mounted on a 3D print that's epoxied into the inside of the parachute bay that the AV bay sits right against so that we don't get any leaking between the coupler and the main airframe. So this has worked with our numerous rounds of ground testing, and the reason we've done numerous rounds of ground testing is because this was a concern point, but we were able to find a solution to make sure that our parachutes deploy consistently.
How'd the O-ring work? That's something I've been thinking about for years.
It was originally, it was a little bit hard to get it nested properly. I guess actually, I apologize. The way that we have it is we put it on the AV bay, not with the additional attachment, I believe, Barry. Correct me if I'm wrong, but
Yeah,
I think the hardest part was getting the fit correct. Because if you don't have your dimensions right between what your O-ring's sitting in and your outer body ring, then it does nothing. So we had a few times that we were relying too much on our O-ring and it wasn't properly nested. So I think one, making sure all of our other fits were good so we weren't relying too heavily on the O-ring. But then also making sure that our 3D prints were measured properly. It now works. I'm not sure how much of that is O-ring versus all the other changes that we made. But that was one of the changes we made right before our first successful ground testing. So
Roger that. Okay. Yeah, I'm good with it. We had multiple conversations on email about this, so
okay.
I'm good.
cool.
So you can go to the next slide. Or it might just be lagging. Okay, perfect. Sorry, it might be lagging on my end. Fin attachment. So because this is our first time as a club going supersonic, we were concerned about fin flutter this year. So we were also trying to make sure that we had narrow, we had thin fins to allow us to reduce drag. So the way that we manufacture our fins is we did a carbon fiber layup, just flat pre-preg, and then we cut those to shape. And then we used a table saw and a beveling jig to cut an 8-degree bevel from the edges. I'm really sad that we don't have a picture. I mean, it's not useful. It looked really pretty. Side notes, not needed. But so we were able to get that 8-degree bevel. Ideally we wanted, oh my goodness, I'm so sorry. I need to stop working 9-hour days. The shape. we wanted it to be a more curved shape, but we weren't able to find a way to manufacture that. So our 8-degree bevel was the best way we could kind of reduce the drag on our fins while still keeping its structural integrity in terms of manufacturing methods. We then, in order to attach the fins, epoxied them to the inner tube. We had a 3D printed fin jig to fit our exact dimensions of our inner tube and our fins in order to make sure that our fins were perpendicular or normal, I guess, to the outer airframe. And then once we epoxied it to the inner tube, we then did a tip-to-tip fiberglass layup onto the inner tube. This was chosen, typically tip-to-tip layups are done on the outer outer body tube. But we were trying to do on the inner body tube just so we don't have any problems with outer surface finish on our rocket. So we did, I think, 3 layers, 2 layers, thank you, fiberglass, tip to tip on all 3 connected surfaces in order to make sure that our fins were stiff enough to go through that supersonic transition region. And then we cut our fin slots into our body tube, and this is a picture of just the inner tube with the fins attached, and then the outer tube gets slid over the whole thing with the fins going through the pre-cut slots. And then exterior fin fillets were done with silica reinforced epoxy so that we have the shape that we're expecting in terms of the outer airframe of the rocket, but then also we do have an additional connection point to help with our fin stiffness. And I believe Tyson is talking later, or maybe I'm talking later. I think it might be the next slide actually, for talking about fin flutter analysis that we've done.
Yeah, I think we'll throw that over to Tyson to talk.
Okay, perfect. I read that slide like a few times and I was like, I think I know it, but I'm not going to know as well as Tyson, and that's embarrassing to present in front of him. So.
Copy. Yeah, I know we had multiple. This is another topic of conversation between us. So.
Okay, perfect. Any questions on?
No,
here,
I
you
like
already are pretty covered.
I like the way you've done it. It's important to have both attachment points, both on the inner tube and the outer tube, be very strong, and it's obvious you've done that. So,
Yeah.
the tip-to-tip layup on the inside and the fillet that I see that you've done, it's going to be solid.
Perfect.
Oh, it's thrust plate and then it goes to fin flutter.
Okay, perfect. I can do thrust plate. I do know this one. Okay, so our thrust plate, as I was saying earlier, well, I guess I did say this part, but our motor is huge. It scares me a little bit. And so we did not want to have to do our normal thrust transfer method of just a bulkhead. And so in order to try to make it so all of our thrust is transferred through surface-to-surface contacts, instead of epoxied contacts, we are using a thrust plate this year. However, we still did want a tail cone because we have found in the past that one makes our flight path more reliable in simulations, but 2 also just improves our apogee in general because we're able to cut down on drag a lot. And so we have this kind of unusual looking thrust plate. The idea is that on the base, you see your normal thrust plate, and then we kind of extended it so that we can hold the motor a little bit further back from the rocket, allowing us to have a tail cone without the flames getting in the way of the tail cone, but also allowing the tail cone to not need to be a structural piece, as all of the thrust is initially transferred directly to that first carbon fiber airframe piece. We have done extensive FEA on our thrust plate to make sure that we are good. Safety factor is 1.74. And is attached to the rocket using more M4 bolts. These will screw into inserts in the plywood centering ring at the base of the rocket. The other thing to note is it is entirely solid aluminum except for those cutouts that you see at the base, which again, those were tested using FEA simulations. We are confident that those cutouts will not decrease the strength of the thrust plate below what's needed. And then the connection joint is welded, so it will do well in compression, and we have no concerns there. Another thing of note, just so you're not suspicious of it, is that top ring is to just help ensure the fit of the motor. We want it to be a tighter fit and to reduce wiggling. And so that's pretty much the purpose of that top piece there you can see in the picture. And then, yeah, the boat tail just slides over top of this, and the boat tail does not need to be a structural piece, and that is why it's fine that it's just 3D printed. Any questions there?
No, looks good.
Perfect. Next slide, Barry. Okay, perfect. And I'm going to turn this over to Tyson. This is his area of expertise.
Okay, perfect. Thank you. So we did a bunch of both numerical analysis for our fin flutter, and then we also did roving hammer testing to verify that all of our assumed properties of this lovely carbon fiber that is donated to us is actually what we're getting in our physical model. So this is another fin that was cut out from that same batch, attached to a separate biotube that we tested it all on. We verified everything. We used MATLAB. We got beautiful pictures of all of um, the modes of frequency for both torsional and bending. And we calculated a max fin flutter of about 4,300 feet per second, which is more than double what our predicted max velocity is. So we are very confident that we will not have any fluttering on this flight, and we are very excited for that.
Yeah, I'm good with this. We had multiple rounds of back and forth of talking about fin flutter and the fin design, and what I'm seeing here, and based on our conversation, I don't have any concerns.
Okay, perfect. Thank you.
Okay, perfect. I can jump back in here. So our counterweight system, what's helped us in the past to be able to nail our apogee, is to be able to adjust the weight of our rocket day of launch based on weather conditions. Which in the past we've had a coupler dedicated solely to the counterweights. However, this year, because we were trying to shorten our rocket, we've integrated our counterweight into our motor mount tube. And so our counterweights are located directly at the center of mass of the rocket so that we can add weight to the rocket without having to concern about rebalancing the rocket with additional weight in the nose cone, which is what we've done in years past. And we have a kind of centering ring coupler situation epoxied into the rocket. So the coupler or the airframe already has to detach right around where the counterweight system is. And then we have kind of donut-shaped weights that will slide around the inner tube and go inside of our outer airframe that we can then tighten onto threaded rods for this counterweight system. Each plate weighs about 3 pounds. So we have a little bit of lower resolution, I guess, in terms of the weight that we can adjust. But we also have a decent amount of space on those threaded rods. So we'll adjust the weight more as needed, just using nuts added to that. And yeah, the nose cone, I'm realizing the variable mass is no longer relevant this year because we were able to move our counterweight system to be right on the center of mass.
Okay, yeah, 3 pounds is a large amount. It's not a lot of fine tuning right there, but
Yeah.
you're
But
gonna
then if we have one, we normally will do with smaller weights, but because we're going to such a high apogee this year, we needed a very large weight range, just because of, since we're going further, there's more room for air, I guess. So yeah, we went with the larger weights, and then hopefully that gets us close enough to be in an acceptable range of what our target apogee is.
And if I can add one thing there, the decision to do these 3 pounds was done with some Monte Carlo optimization through Rocket Pi. And we basically discovered various bubbles per se for what we needed to hit, for basically various bubbles of environmental conditions. And those actually happened to be very close to these increments that we were hitting on. So basically, we either need almost no weight there, or we need about 3 pounds, or we need about 6 pounds, and that's about what we need.
Okay, very good.
Any questions there or concerns about attachment methods?
No, I like
I guess
the
I didn't
idea.
say, again, these are epoxied in and through wall bolts.
Yeah, that's fine. I like the idea of putting them. It reduces complexity when you put them near the at the center of mass. So that's a good idea.
Thank you. Awesome. Thank you. Next slide. Sorry,
right.
my computer's lagging. Okay, or yeah. Sweet. And I'll
Cool.
turn it back over to Barry.
All right. We'll talk very quickly more about the motor that we're using. I've already mentioned that it's an Aerotech O5500X. But just so you get an idea of what we're playing with here, and you've probably talked to some other 30K teams that are using similar motors. We have a total length of 55 inches, give or take, 55.44. So it takes up about half of our rocket. So one of the things that we had taken into account was we decided to go with a split inner tube design just because we couldn't solely manufacture one inner tube that was long enough for this motor. So we essentially have two separate inner tubes that have like space in between them. And we have a 3D printed a little, we had to 3D print a little jig to allow us to be able to slide the motor into the other tube just because it's not, it tends to wiggle a little bit. So with that 3D printed insert, it works just fine. We have an average thrust of about 1,200 pounds. The maximum thrust we experience with this motor is about 1,700 pounds. And burn time again is 4 seconds. And then you can see a thrust curve right there. So any questions about the motor in general? It's pretty
You
simple.
fired. This is your first O motor,
Yeah, this is our first O motor.
and Brett, you fired something like this before. Are you familiar with like the instructions on how to use it? Just curious.
Yeah. Yeah, I've built and launched one of these, so I'm aware of it, and I have 4 other teams using this motor. So
Oh wow. You have 5 teams?
I'm flyer record for 5 teams, and
Oh man.
I'm doing 9 safety reviews, so it's been a tough week.
I have 5 safety reviews and I'm flyer record for 3 teams, and I thought I had a bet.
Yeah, well, I'm sure somebody else is doing more. So,
Yep.
so we've talked a little bit about assembling this motor. I think the guys plan to assemble it in their lab and drive it down assembled, which
Yeah,
I think is prudent. I think I had recommended to them they put it in a big anti-static bag and then wrap it with padding. But
I
if
don't remember
you
you
didn't
saying
say
that.
that, I will say it again.
Okay, get noted.
So I buy them on I buy them from McMaster, and I put 2 bags, one on either side, and wrap it up tight, and then I put it in big moving blanket. So that could be a way to do it. Be sure that you let the grain set overnight before you glue in the top closure. So yeah, it's 2 full days of epoxy cure.
Okay. One thing to note is I won't
And I'm
be,
happy to go through it more with you guys if you want.
I would appreciate that. Sorry, the cat is messing with my laptop. One thing to note is my plan was to assemble the motor the day before we drove down for IREC. So if you're saying that we need 2 days, then we'll probably need to push that back a little bit.
Yeah, so you need to get the grains in. You take pairs of them with 30-minute Bob Smith typically, and then you use Gorilla Glue probably for the liner bonding. I like to let that set sitting on a flat so it is stable and done. And if there's any foam up, you clean that out before you put the top closure in and then epoxy that down. So I would recommend you do it with 2 full days. I suppose you could rush it, but the consequences of Cato's of this, you really don't want to rush it. So I would leave 2 days.
Okay,
Yeah,
noted.
I'll be around. I can help with that if we need.
Okay, cool.
And
I
I
don't
and
get any.
I've assembled a bunch of our M motors that we've done, and so like I'm comfortable enough with the assembly idea that I can help deal with that. And I'll talk to you more about that as we get closer.
Then
Yeah.
let's coordinate that then.
Yeah, so at least a week before you're going to do this, maybe Barry, we could chat a little bit more, and I could give you a couple of ideas of things that you might want to have ready to
Yeah.
make it easier.
Cool. Yeah. Let me mark that down really quickly. Just note to myself here.
You could drop by my shop while you're driving before I leave if you want. We could assemble it here, but you'd have to wait 2 days in Santa Fe, which you don't want to do.
Yeah. We're gonna try to do it all in one. Anyway, we can coordinate this later. Sorry. Well, we'll keep on moving, Brian. Thanks for giving us a moment to talk about that.
Yep.
Yep.
Just to finish on motor, uh, What igniters are you guys planning? I forgot to ask you this earlier.
So I purchased two Wildman
Yeah.
Wildman igniters.
Cool. And are you using sticks or are you going to put them on the cardboard too?
Plan is just to use sticks.
So you're bringing sticks, or do you want me to give you some? Or
You can bring sticks. I'll just get some wooden dowels.
yeah, 1/8 inch dowels. Yeah,
Yeah.
48 inch. Okay,
Yep.
cool. Tape them once, every foot.
Yeah, I only bought two.
Yeah,
But
that's great. All you need is two.
yeah. Talk a bit about arming electronics here. Don't have any pictures. We have the electronics there in person though, so if you want to look at it later, we totally can. We're using two altimeters, both of which are Blue Ravens. They're each connected to their own limit switch for activation. Each one is also separately connected to its own CO2 deployment system and paracord cutter system, along with its own battery pack. We plan to use 35-gram CO2 charges, and Bryant will talk more about the specifics of the systems when we get to the avionics bay.
Yeah, I read your report. You said you're using, it was a 23 as the primary and the backup is 35 or something like
Yeah,
that?
we decided to just go to 235s.
Okay.
Yeah. And then for the GPS, we're using Featherweight GPS as our primary. We have a SRAD through a Pixhawk as our secondary, both of which will share the same battery due to weight concerns we had of hitting our apogee.
And then you tested that, right? With
Correct.
you did drain testing?
Yeah,
And
we
you
did
like
battery
5
drain.
hours.
Yep. 5 hours. We've also done range testing. So we had one person just hike halfway up a mountain. We had another person just drive like, I don't know how many miles out. It was like 10 miles out and try connecting to them. And they could. So
And you got that range on both of those systems?
Bryant, got range on both those systems.
Okay. Because the 5 hours is good, but if this thing lands, in a place that's either difficult to get to and you're dependent on a secondary GPS hit, it may die before you get that. And so you may
Yeah.
end up doing a lot of searching in the brush.
Yeah. Bryant, really quickly, can you talk to battery time on each one? I'm pretty sure those are 5 hours, but I just want to confirm.
Yeah, both are 5 hours. Yeah, sorry, was there any more to that question or just that?
Just
No.
battery time and then also range.
Oh yeah, okay.
Yeah.
So the Pixhawk, what's interesting about that is the main intent of that is for use with live telemetry. And so that was the main impetus in including that device. And so that one we were able to get to a range. I don't have the number exactly right in front of me, but it was 28,000 feet, which is less than the Apogee, but that one will be using a human auto tracker, aka me with an antenna pointing it. And so the intent of that was just a proof of concept to iterate on a previous design to learn how live telemetry works and how we can use that. But yes, the Featherweight is commercial off the shelf. It is supposedly good to 300,000 feet, but we tested it to a distance of 10.8 kilometers with absolutely flawless connection. So
Okay.
that one is definitely 100% ready to go. The other one is experimental and is hopefully going to teach us a whole lot about live telemetry.
Very good. Here's my system. Anyway. Very good. Next.
Cool. All right, for the arming sequence, we plan to arm the Featherweight GPS and Pixhawk first and begin the connection sequence. That will be prior to the rocket going vertical. That'll probably be while we still have it in the tent with us. Once the rocket is vertical, then we plan to arm altimeters one at a time using pull pins, listening for the expected readouts. We'll also arm the payload using pull pin. Kind of at a safe distance since it's also relatively experimental. If we're using 3D printer again, there's resin systems in there. And then plan to insert the igniter into the motor and check for continuity. So pretty standard procedure, I'd say, for most of this.
Yeah. Your pick sock is not, that's just telemetry only. It's not doing any activation like pyros or CO2 or anything like that, right? Yeah. Okay. That's a lot easier, a lot safer. You know,
Yeah,
it takes a long time to develop one of these things, and to get the coding right, but
yeah,
less less risk when you're not doing any events. So
yeah, yeah.
I'm
Our
good with
thoughts.
this.
Cool. All right. Now here to talk more about our payload is Andrew McDonald. So Andrew, if you want to take it from here.
All right. So this year's payload is a iteration off of last year's design of a compact, robust 3D printer. This year, we've made several improvements, including reducing the weight by about 2 pounds, improving the electronic systems, adding more robustness, and addressing a lot of concerns that we ran into last year. The For power, it will run off of four life batteries that will just drive the system at 12 volts, and should give it a sustained battery life of 2 to 6 hours, depending on um, if the system is active or not. But again, it's a
LIFE batteries. I've heard of these, but
yes.
I've never seen a team use them.
Yeah, well, with the payload competition, they have pretty strict regulations on what batteries you're allowed to use,
Yep.
and the life batteries are so safe that you basically have to have no additional like safety measures to ensure that like they don't damage other parts of the rocket or explode or something. So that's our reason for deciding to use them, even though they're a little bit less energy dense than other batteries. But the payload will be inert, running off of a simple microcontroller that will use a IMU to detect when the rocket has landed, and then when it's landed, run a simple 3D print.
Okay.
Next slide. All right. Right. Yeah, so this is kind of just walking through how the payload will work. We'll run through a pull pin, which will be attached once the rocket is on the pad. Um, the Once the rocket is ready and all the other pull pins are pulled, it will also be pulled. That will keep it off, but with that microcontroller on to detect when launches occurred, so that it can detect when landings occurred. And then once the rocket is landed, it will execute a print job while awaiting recovery. And then once the rocket is landed, the rocket is recovered, the print should be complete and the part can be removed, demonstrating its robust 3D printing capabilities in any orientation.
We'll see if it survives the O5500.
Yeah, we definitely put a lot of thought into that, especially using the information collected from previous tests. Some of the parts that were slightly damaged from last year, and then all the parts we made this year were designed with those specs in mind. For example, the base plate, which I left on the other side of the table, but
It's actually not the motor that's going to get it. It's probably the main opening. It's actually the
oh,
single most significant G load event during the
mhm.
entire flight is the main opening.
Oh yes, the sudden tug there. Yes, our the base plate we ran simulations. It's using just a single bolt attached through a bulkhead, and we've believe had a safety factor around 2.5 for the loads expected on that pull through. I don't know if 2.5 is an exact number. I wasn't running those simulations. But um, and then with that, the rest of the base plate is the part that's experiencing the loads, and so, but the rest of the rocket, so the rest of the payload is supported with four carbon fiber angle brackets that through testing have had the same, have been able to withstand the compressive forces or sorry, I'm an electrical engineer. I don't always know the technical words for all the different types of loads, but it will withstand those loads through our testing. And then the top is also in aluminum. Again, it's not expected to experience loads, so it will more meant to hold
Okay.
everything together. Yeah.
Very good.
Do you want to address any of the safety concerns, Andrew, about this? Mainly the resin, that's what I'm thinking about.
Yes. So the resin will be in a contained container. Sorry, contained container. It will be in a syringe, and it will the payload, the entire payload will also be enclosed in a tight 3D printed shell, and so any leakage, which will be
Is it toxic or
minimized with
something? Is it toxic or something?
Like touching with the skin, yes. It's not like extremely hazardous, but I mean, can cause skin irritations and certainly isn't good to like drink or anything.
Gotcha. Okay.
But there's two levels of containment with both the syringe and the case. And it will also be there will also be foam pads absorbing some of the vibrations for a lot of the sensitive equipment like the electronics and the syringe system. Sorry, rubber pads, not foam pads.
Yeah, specifically speaking to those pads, it's basically we just take a EPA foam, we cut a hole in it, and we slide it around the payload while it's installed in the rocket. It just prevents it from wobbling back and forth.
Yeah.
And
Okay.
fancy.
Yeah, and I was also talking about there will be rubber pads under, again, like the electronics and stuff to absorb some extra vibrations as well. But yes, the entire plate will also be encased in foam.
It's a neat concept.
Cool. All right, recovery, Bryant, we'll switch it over to you now. Bryant is our GNC team lead who has been doing a lot of kind of leading the charge on using CO2 and single bay dual deploy and using a lot of systems we've never touched before. So I think he's done a lot of great work here.
Cool. Thanks, Barry. I'm ready. Okay. So first of all, just want to reiterate that we are doing dual deployment from a single bay. This is something that we haven't done before, so we've done a lot of testing, couple test flights to be able to ensure that we're actually able to do this. And we've gotten a lot of help from Brett, just trying to figure out the finer details of everything that we're going through here.
Yeah, I saw your video. It looked good.
Okay, great. Thank you. So we have a 96-inch main parachute. It's an elliptical shape, so coefficient of drag of 2.2 just lets us have a much lighter parachute for much greater drag, which is great. And then we have a 36-inch drogue that's going to deploy at apogee.
Okay. Yeah, we talked about this multiple times over email.
Perfect.
I'm good with it.
Cool. This is a picture you'll see on the next slide. There's an exploded view of the avionics bay. So if you want to, pick anything apart, then we can go to that slide. There's a lot going on here. So I've tried to kind of label everything. But we are using two completely separate systems with two separate Blue Raven altimeters, both of which have their own 7.4 volt lithium ion battery. And each of them is connected to screw terminals that are on that top bulkhead. And then those screw terminals will connect to both the CO2 Raptor system and the Mako cord cutter system, which are both on top of that bulkhead there. You'll note neither of them are fully constructed. Both of them are missing the caps that will house the black powder and the implements for doing the task that they're supposed to do. The Raptor has a pin that black powder will ignite. and force the pin into the head of that CO2, which will release it into the coupler above it. And then those cord cutters will blow a piston through those cords and take care of that. As far as shear pins go, we're using 440 shear pins. We have, I don't remember the factor of safety on that for separation due to pressure differential inside of the parachute bay. However, we do have vent holes in the parachute bay to counteract that, and we do have a factor of safety. And then that has also been verified that for 440 shear pins, we're going to be able to blow that off with our 35 gram CO2 charge.
Hey, Brian,
Yeah, sorry.
I had just a small question, if you don't mind. Looking at the av bay, I think I see batteries that are attached with a single zip tie. Is that what I'm seeing there? It's not close enough up, so I can't see the.
Yeah, that's not final design. Our plan is to attach them with 3 zip ties. This was just setting it up for ground testing, trying to minimize waste of materials that we were using. So we're planning on using 3 zip ties for each of those batteries.
You're going to do that and you don't have any standoffs. I recommend you talk to your flyer record. One thing that may help is having like double-sided tape on the back of that. Not a loop of masking tape, but like, the M3 double-sided tape.
Yeah, I use servo mounting tape is another
Yeah,
good.
that would work too.
Yeah. Um, so I would say those batteries look like they're too flimsy and hanging in the breeze. So we need to beef that up. So maybe we can see that when you're all done. Not today necessarily, but when you have the final version.
Okay. Sounds good. Yeah, we'll discuss that, figure that out.
And where are your GPS trackers? Are they in the avionics bay? I don't see them here.
No, both of them will be up in the nose count, and that'll be a later slide.
Okay, very good. And what's the transmit power on your Pixhawk?
Trying to think.
Because I know the featherweight uses low power. It's the LoRa modulation, but the Pixhawk is something different. And I had literally have seen rockets fail because they had avionics right next to a transmitter that was transmitting at 1 watt of power or greater, and it caused failures due to EMI.
I don't have those numbers for you right now. I'm not exactly sure.
Yep. Even if you have both of them, I would check the wattage on that thing, and then I would check, I'd operate them both at the same time and just verify that they're both functional and one's not interfering with the other. The LoRa is most likely not going to interfere with your Pixhawk. It's the Pixhawk and at what power it could interfere with the commercial system.
We did, just as like a side note with this, we did fly with the Pixhawk and the Blue Raven last year without any of those issues.
At the same power?
Yes.
Okay.
Yeah, and I guess we have done distance testing, and we were able to use both of those systems simultaneously. We tested them simultaneously, so hopefully that won't be a problem, but we'll definitely keep an eye on it and do a little bit more research into that.
Okay. It's really the power that is what matters.
Okay.
And then a little bit of the design. I have seen some EMI at low power, but it really depends on, tracing placement and all sorts of interesting, electrical design.
Okay, sounds good. Let's see.
I see the electrical engineer smiling.
Yes. Last couple notes. We printed this out of PETG. Our plan was to print it out of carbon fiber nylon, 3D printed, but we weren't able to get into the materials lab and have that done just because it requires special whatever. So we decided to go with PETG just based on its strength properties and heat resistant properties. And we're confident that we'll be able to operate without any issues with that. And then we have 1/4-inch vent holes for the for altitude readings and barometric pressure sensors and whatnot on the inside.
Blue Raven's less susceptible to this, but where are your vent holes on opposite sides of the rocket, or are they right next to each other on the same spot?
They're opposite sides of the rocket.
Good.
Yep.
Sometimes with a strong wind, you can get buffeting and pressure differentials, and in the past, avionics have been tricked. It's less of an issue nowadays, but it's always
Okay.
good practice.
Cool. Yep. Opposite sides. Barry, you can go ahead.
Did it look like I was about to say something?
No, sorry. I just meant next
Next
slide.
slide.
Yeah. Sorry. This is that exploded view that I was talking about. If you have any questions, we can come back to this and I can break it down for you if you'd like.
No, I'm good.
Okay, cool. So we did a lot of ejection testing. Lots of CO2 charges got burnt this semester, and it was really fun, but it was a lot of money. So we're happy that we did it. We wish that we just knew more, but this is for future club, right? So we had two rockets that we either altered to fit the CO2 and cord cutter ejection system or made from scratch just to test the system. The first one was Escapito. We just wanted to just fly it and just see if it worked with CO2 and cord cutting. And we talked to Brett a lot, and we were successful in launching the rocket. CO2 separated, the cords cut, or the cords were cut, but due to an operator error in folding of the parachute, we had tangling of the parachute, and Escapito was damaged beyond recovery. But it showed us a lot, and it showed us that both systems were working and that they were working. It was just a minor oversight that caused that issue. And then our second rocket, Hephaestus, we wanted to iterate on the mistakes that we made there. Everything was effectively the same. We just tweaked a few things, moved parachute locations a little bit, and we also we had everything basically in the same configuration that it is currently in Escalante. And that one, absolutely no issues, resulted in a successful recovery. Everything worked just as intended. And
Yeah,
then
the
we've
video looked
also,
good.
thank you. We've also done multiple ejection tests on Escalante just to ensure good separation and working electronics, and also that seal that Haley talked about, which was probably the most finicky thing about the whole project, but it is working now, and we're confident in that.
All right.
And then I just put a video in here in case you wanted to see another ground test, but I think we can move past that.
Yeah, I saw that. I want to get to the rocket soon.
Okay, cool. We'll try to zoom through this then.
Yep. Most of the stuff here is pretty standard. With our shock cord, we have 42 feet of shock cord. It'll only be one single length of shock cord since we're only doing one bay. We talked about the parachutes already. The main chute is going to be contained in a parachute bag, and nothing is exposed to black powder. All of it is contained. The black powder is contained, so we're not really worried about fire protection. We also wanted to get rid of that anyway, just for weight reduction. And then on the right, you can see what everything is rated to. And we have good factors of safety on everything. The eye bolt is the weakest thing that we have throughout our entire setup. And under absolute worst loading conditions, we have a factor of safety of about 2.5, but that's assuming 40 Gs of acceleration, and that the rocket maintains 76 pounds for its entire flight at that 40 G event. Under normal conditions, normal main separation, we have a factor of safety of 5.5 on that. So we're pretty happy with that. Everything else is way, way higher. That was just the point of concern that we were worried about.
How are the ends of your recovery harness done? Are they sewn together? Are you doing a knot, a loop?
Yeah, we're doing a figure 8 knot. It's one that we've been told to use, and that we have experience with in the past, that it is of high strength, and it's good.
Just one on each end.
Yes.
Okay. Very good.
Okay, so this is that slide I promised you. We let's see. So it's a little bit of a mess to look at, but we have Pixhawk with the GPS module. That's that circular piece on top, and then next to that is our featherweight tracker. On the back is the radio transmitter module for the Pixhawk, and then also that battery that they both share. There will be a wire that is running down to right above the AV bay with just for limit switch to be able to have all of our limit switches in the same area, all of our pull pins, since we weren't able to put it through the nose cone here. Let's see. On the left, you can see the different specs of the electronics that we're using. The Holybro transmits at 915 megahertz, and then our featherweight tracker will be using 923.8, and that can be varied very easily by just using the app to change that frequency. Also, in this, actually, hold on. Okay, yeah, sorry. This is also 3D printed PET-G, and then we have, it's not shown here, there will be a small receiver module for our remote start camera system that will be right where the green and white wire with the tape on it is sticking out. That will be the receiver for that camera system, just so that we can turn it on, turn it off from a distance and not have it running for a couple hours, which we're hoping will help us get camera footage. But all of that will be on those two faces. And then the electronics, wires, and a buck converter are on the inside of that
Okay.
plate. And then this is the exploded view of that.
Yep. I'm good.
Okay. That's end of my section. I don't know if you have any other questions about recovery or anything.
Nope.
Okay.
Yep. And I'll just run you really quickly through all the tests we've done, and then we can get straight to the rocket. Just a quick overview. So we've done compression testing on the carbon fiber tubes, done compression testing on the carbon fiber angle brackets themselves. We did a laser vibrometer analysis of the carbon fiber fins for fin flutter analysis. We've done ground testing and for CO2 and cord cutting. We've done payload resonance system testing. We've done altimeter sensor testing. We've done battery drain testing, telemetry link testing, and GPS link testing. And then we've also done R2 L2 flights as well. So that's a basically complete summary of all of the physical tests we've done with this rocket.
All right. I'm good.
Cool. And then there's a contact page. That's it. Want to get to the rocket?
Yep.
Clicking off all the rest of the things we have left.
Yeah, so it'll be a little bit random. We'll go from the top to the bottom if it's okay with you guys, but I'll call out some questions on my checklist that we haven't covered already. So just hang tight. I gotta get a pencil.
Yep, I'll stop screen sharing.
All right, you show me the nose.
All right, Andrew, this is you.
It's all well, so
Lost him.
I lost connection immediately. Wonderful. Why did it do that?
It's called Murphy's Law.
There it is. All right. So there's top of the rocket. What are we showing first?
Can you disconnect it and show me like the avionics bay? I know you showed me pictures of it.
You'd have to unscrew it, Andrew.
Oh, just the nose cone?
Yeah.
Is it screwed?
I mean, you showed me pictures of it, but typically we would tear it apart and take a look at everything.
I think they left the screws in for it.
How long is that shoulder that holds the nose cone in?
6 inches.
Okay.
Okay. Sorry, I'm trying to think how I can show this and also. So it's the nose cone. I think these screws hold it together, right?
Yeah,
Yeah.
just take those out.
Okay. Let me find a screwdriver for that because the one I have is a little too small.
Andrew, typically the screws closest to the seams on the body are the ones that hold the seams together.
Okay.
I think. I'm trying to think if there's any seam that's not the case.
Sounds
If it looks like there's epoxy around the screw, don't do that one, do a different one. But otherwise, it should be the one closest to the seam.
It's the top one. Yeah.
And then when you showed me the pictures of the telemetry bay, um, you know, double check just like we talked about with the batteries before, you know, take a look at I saw 2 zip ties on those. Consider doing more, consult your flyer record. It will get attention at the check-in, so you know, you're pulling 16 Gs. That's a pretty decent amount. So you know, you definitely don't want to lose any light avionics just because your battery's tore loose, and especially since you've got a single battery for both your GPS telemetry systems, it's extra important that that one not fail.
Yeah, for sure. We'll work on that.
I'm mostly looking here for the shoulder length and then to just kind of verify that it looks like what you showed me in the pictures.
Yeah.
We talked about the shear pins. We talked about the material of it. It's all good. And then, you know, the questions I'm asking about the avionics, that's the other thing on my checklist.
The avionics are already out of the rocket, so that should be easier.
And then in that upper bay, or actually you've only got one bay. So you've got a vent hole, right? So you're not carrying that, you know, 1 atmosphere of pressure up to 30,000 feet with you.
That's correct. Yep.
Okay. It doesn't need to be huge, just needs to be there.
There we are. All right. See if I can wiggle it off. There we go. All right. It's the nose cone.
Yep, I can see it. And then show me down on the inside. And how is that how is your avionics, the GPS trackers, how are they mounted in there? Are they going in those little, or are they going to something else?
Believe
It's a threaded rod that goes attaches through the metal tip of the nose cone all the way down that it is center mounted and lock nutted on.
That's what that was. Okay, I thought that was a very interesting looking GPS antenna. It was not the antenna. It's the I got you.
That's good.
Okay.
Yeah. So that, just for additional clarification, that like fiberglass washer on the top nests into the nose cone, and then the structure itself is also compliant, so it holds itself in the nose cone. And then the metal tip screws on the top on the outside.
Okay, and how are you securing that? Are you going to use Loctite or just hand tight, or any chance of that? It's going to heat up a pretty decent amount. Any chance it's going to wiggle loose?
I don't think we have any plans. We can probably add Loctite to the assembly.
I thought we did Loctite last year.
Okay.
All right, yeah, something to think about. It's going to be, you know, the temperature cycling on that thing is going to be pretty extreme, and so it could come loose even if it's just hand tight. Okay, I'm good with the nose. Body tubes. We talked about the construction. You guys did the testing. Did you do any? You did the compression testing, but did you do any lateral compression testing? Like put it on its side and try and squeeze it? That's usually where I see the student build tubes fail. Because if you didn't, and I think we talked about this, if you didn't put some of the hoops in there, sometimes it can be, you know, really strong this way, but this way pretty weak. And then with a little bit of wiggle on the flight, you know, that's where you end up with a banana rocket at Mach 2. that doesn't stay a banana, it shreds.
No, we did not do any sort of lateral testing this year. But one thing to note is we've made the most bottom coupler, so the coupler that attaches the two body tubes, that one is now 9 inches instead of 6 inches. So we tried to prevent any, I don't know, giving it a little bit more of a moment to hopefully reduce any wiggling there. So that is the precaution we kind of took in place of that. I don't know how
But
satisfactory.
it's the tube itself. So I mean, get two things. So give me a knock on it. Does it ring? Knock on it with your hand. Go ding ding. Oh, I can't hear it.
Oh, shoot. Here. Using
I'm listening to sound if it sounds tight or if it's like a thud. All right, I heard that. It sounds like it sounds pretty tight. And then just give it a little squeeze. Around it. So it's that, lateral movement. Yeah. Okay. Yeah, that looks. Is it moving at all? It doesn't look like it's moving, but it's in your hand. Okay.
Doesn't feel like it's moving.
I
Okay.
will say if it's any additional consolation, they were all cured in like an actual legit autoclave with some carbon fiber technicians that were very particular about the way we vacuum back things. So everything was held to at least the 27-inch mercury standard after much pain. So it should be all properly cured.
I got you. We always check though. All right. We talked about the vent hole. What's the thickness on that thing? On your wall thickness?
That would be about 0.08 inches.
Oh, okay. So you're longer or thicker than the standard thickness, so you're good.
Right, Haley? Does that sound right? You're giving me a funny face.
That math sounded right, but thicker than the standard thickness. Maybe I just said like I overestimated standard thickness, but I will run the math.
No, that's
Standard
dead on.
thickness is the 16th, so 0.062.
Okay. Okay.
Yeah,
Yeah, that should be good then.
0.08's dead on.
Okay, perfect. Sorry. It's thinner than we did last year. So in my mind, I assumed it was going to be thinner than anything standard, but yep, the math sounds right. I just wanted to check. Good to know. Thanks, Tyson.
Okay. And then show me the where the points where the bolts go into the airframe.
It's into the airframe. That like these points.
Yeah, there you go. That's
Okay.
good. And then
So
Yeah.
there's one.
Good.
This is the upper body too.
and then on the bottom part, it looks like you're good to. So what I'm looking for is what I've seen teams do in the past is like here's the end of the tube, and then like an eighth of an inch below that is where they put the hole. That's
dear.
gonna tear through.
No, we're not even close to that.
Our closest to seam is like 4.5 inches.
Gotcha. Okay. And then you got the team name and the frequency on that.
On the tubes labeled, no, we haven't. That's something that we need to do before we go.
Okay,
Where's the
don't forget.
team name, but not the frequency.
You gotta have both.
I think what he's talking about, Andrew, is on all the tubes, we're required to label each body tube with the team name, number, with the team number and the frequency. So we just need to get a label maker or something and spit out labels and put them on the inside.
Because if you lose a part, like for something separates, and another team finds it, they'll bring it back and they know exactly who it belonged to.
Yeah.
So if you're losing points and they bring it back and it's fine, then you got your points back. All right. Good on the body tubes. Couplers. You guys, what is that made of again? You guys did carbon fiber?
Yep.
Yep.
Same
Yeah,
process.
couplers are carbon fiber and they're twice as thick as the body tubes just because of fit reasons. So
Okay. And basic same method of manufacturing.
those were cured in just a standard oven, not an autoclave. So the vacuum seal was not as good. Otherwise same manufacturing method.
Okay. And I'm not going to have you guys bang on it and check, but it's, basically the same level of stiffness and tightness.
Yeah.
Okay. And it's epoxied in, or is it You guys got screws in to hold in one spot.
So
All
for
of them have all of them have through the wall screws.
Okay.
there
Very
will
good.
be there is one coupler. They all have through the wall screws, but one coupler attaching the lower booster tube to the upper booster tube. The bottom half of it is epoxied in place.
Okay.
That is using West Systems 1050.
Perfect. Talked about the harnesses, attachment points, length, thickness, all that kind of good stuff. We talked about your chutes. We talked about your drogue, the size, your descent rates. We talked about your shear pins. You got four 440 nylon shear pins. You're using CO2 at apogee and BP at the main. Is that correct?
No, main is using core
Oh
cutting.
yeah, you got the separation. That's right. And then you talked about your hardware and your quick links, hard points, all that kind of good stuff. Talked about your electronics. I'm good there. More to beat that dead horse. Talked about your motor. You guys got your igniter ordered. We talked about retention. How are you retaining it? We talked about the thrust plate, but not necessarily the retention. How is it retained?
Retention is through the top.
What do you mean through the
So
top?
we have a bulkhead that we're threading it into.
So
Forward
you
motor
have
retention.
a piece of all
Yes,
thread that goes
sorry.
into the forward closure, and then that goes through a bulkhead, and then you use a nut or a bolt or
It's the eye
Yeah, I
bolt.
believe it's the standard eye bolt that's suggested by the manufacturer of the motor.
okay. And then that bulkhead is made of, is that a plywood bulkhead?
That's a plywood with the carbon fiber reinforcement.
Gotcha. That's right. You talked about that. And then you've got some sort of washer on there so the bolt doesn't try and tear through.
Yes.
And
Yeah.
that bulkhead is mounted how into the airframe?
Epoxied and through wall screws.
Epoxy and through wall. Okay. And then is it a on that U-bolt, does it your shock cord directly attach to that? Or that's right, it doesn't do it doesn't have an attachment because your avionics base it's above it, right?
It's really weird.
Yeah. It's a little different because you're doing the one tube. That's right. So okay. No, very good. As long as that thing's not going to fall out. That's the concern. So
Can you show us the rail buttons?
Don't know if they're attached to the body right now because of the vinyl wrapping, but I can go find them.
Okay. If they're not attached, so be it. How did they attach?
Wood screws. They go through centering rings.
So they're screwed into the centering rings using wood screws.
Correct.
Okay. How far apart are they roughly?
So here's the nose, and then here's the rail buttons.
Okay.
have you fit them onto a 1515 rail?
Yes.
Have you done a test fit?
Yep.
Approximately how far apart are they?
Yeah, I'm trying to think of a good approximation off the top of my head.
60 inches.
Thank you, Tyson.
So why so far apart?
It's actually like 55 or something inches. It's like 4 inches from the bottom of the rocket and then just above the motor. It's just the length of the motor.
That's where you had centering rings, probably.
Yep.
Okay. Sounds good.
But our off the rod velocity is fine though, so we weren't too worried about it. Originally we had 3. That's what we did last year, but we had a high enough off the rod velocity that we were fine with the placement.
Okay. Sounds good.
Okay. You guys talk your payload stays in the rocket, right?
Right.
Okay. So it's not deployed. We talked about your arming system. We talked about all that good stuff. Weight and location is good. Good there. And then show me the fin can, like show me some more of the rocket. Nice. I like the paint. Or it's a wrap, isn't it?
Yeah. We did not feel like painting that.
And it helps with our surface finish because we can just measure it and throw it into all of our simulations and know exactly what we've got.
Yeah. Yep. Very good. Okay. Let me look at my checklist real quick. Can you give me a tap on it? Though it's got the wrap, so it might be a thud. I can't hear it.
Trying to get it loud enough for Zoom to hear.
It's probably filtering it out.
Yeah, probably.
So does it sound tight? I'm assuming yes.
Yeah.
Okay. Talked about your fin material, the attachment method. We talked about your fin flutter. We're good to go. Talked about your motor tube. It's an interesting split design. Centering rings were good. You got a really good design for a thrust plate. We just talked about your motor retention. We just talked about your rail buttons. We just talked about the effective rail length and your boat tail 3D printed, but it's not a force bearing structure. So that pretty much completes my checklists. Before I go and I talk about kind of like your transportation plan and things to think about out there, do you guys have any questions for me? Brett, do you have anything that you want to see on the rocket?
I'm good. I have concerns about the batteries, but other than that, everything is looking great.
Yeah, my takeaway from this is more zip
That
ties.
that one looks better.
Yeah, that does look a lot better.
So what about vertically? Do you have a way?
Yeah, they've got one vertically. I
Yeah,
can
I see
see.
it there now. Okay. So that's looking better.
Yep.
Can we see the other side? Okay, what's the what are the batteries for the GPS unit look like? Let's look at those. Could you pull the
Pull
batteries?
those back out again.
Yeah,
The
let's look at
No, he's talking about the
for the
avionics for the
GPS in the
GPS.
nose cone. Okay, so there's nothing there's nothing
Vertical is what he's looking for.
vertical. So I would do something more vertical, guys.
And maybe
Okay.
two, if you're just going to use the zip ties, maybe consider using two because that's a much beefier battery than the others.
Yeah, yeah, it's pretty heavy.
Yep, we can do that.
So going back to what Brian said, Barry, I think I told you this story earlier, but I had a firmware error that caused my rocket to separate at Mach 4 during thrust, and nose cone comes out, and then the shock cord stretches down below, and all of a sudden there's an enormous force with the nose cone pointing straight down. And you'd like to find the thing someday. So don't let the batteries escape on you. Um, you know, put more in there than you ever imagined would happen under normal thrust from the motor because it's the bad things that you're trying to cover too. Okay.
Yep. All right.
So I had a question, Brian, about you were worried about the banana, kind of how stiff it is, basically. Is there some standard test to kind of check what the stiffness is? I mean, we tend to make rockets that are stiffer than other people's rockets. Our carbon fiber is pretty good and pretty thick, and the couplings are usually pretty good. But is there some kind of standard test that people use, such as, clamping it at one end and putting a weight at the other end and seeing how much it bends, or something like that?
That's, I don't know if there's a standard test, but looking for that is always a good practice when you're making your own tubes. I had a team, IREC team, a couple years back where that happened. They were learning how to make tubes, and they thought they made a good one because it was like you guys, it was like a tenth of an inch, and it was carbon fiber, and they're like, oh yeah, this thing's rock solid. But they didn't put those hoops in there as they were winding it, that gives it a lot of that compression strength, that lateral strength. And so literally when it took off on an O motor, you could see the photos. You could see it bending in mid-flight. And then as soon as it got supersonic and it's doing this, we called it the banana rocket. Of course, it didn't stay a banana rocket for very long because it just went snapped in half and then shredded into a million pieces. So that's why I ask. But it's a good question. You always want to check for it, especially when you're making your own tubes. All right. You got any other questions out there?
I'm really curious. You said you teams put like this stiffener, like rods or something on the inside of their tubes. I don't necessarily know what you're referencing when you say that.
So when you're winding the tubes, they were doing it with a like a cross winder. So they had a mandrel, and then it's doing the X winding, and it's that 45 degree.
Okay.
All right. But then there's what's important is when you're winding it, doing a 9 degree, wind up a couple of those
Oh, okay,
hoops.
so they're filament winding it. Okay,
Yeah.
gotcha.
It's their filament winding, and so they're doing the 45s, but there's also that 90 degree kind of wind, and that's what gives it that lateral strength.
Yeah. Yeah. These are just pre-preg that we hand roll ourselves, just using sheets.
And so
Okay.
they're oriented in
Yeah,
0 to
you mean
90.
it's a weave, so it has a 50% of it at 90 degrees. So
Cool. Just wanted to clarify that.
Yep. Anything else?
I was just a little curious. So you kind of showed that little PCB that you made. Is that like a custom made like live telemetry system that you designed?
Oh yeah. It's I got at least one team that's going to be flying this, but it's my own design. It's based off of Teensy. It's basically like a Frankenboard. It uses a bunch of breakout boards, and I made a motherboard for it, and then I solder everything together like this is the motherboard. But it's essentially like a Telemega without all the bells and whistles. So because it's got an IMU on there and it's got high G accelerometers, it's 4 outputs. It can do tilt sensing, shut off, the whole 9 yards. I got about a couple hundred flights on it already. The firmware is pretty rock solid at this point. I just need to now turn it into a formal board. So that's the
Awesome.
next step. But
Yeah,
it works
super
really
cool.
well. I lose you guys. I
No,
lost you there.
Everybody's here.
yeah, we're all good.
It says my connection's unstable. Oh, my daughter must be streaming something. Did you catch that?
Yeah, yeah. No, that definitely seems like really cool. Like connecting all that together and doing it on your own. Like every time I like look at the little sensors that they're using, I was like, oh man, I wonder if I could design that. But that's really cool.
Come find me at the launch. If you're really interested and you have the space, you can maybe power it up and do a ride along, and I'll use my 70 centimeter to get you some live telemetry.
Sweet.
Just a thought. I'll bring a couple units with me.
All right.
All right. Anything else?
Not from my side. Good review.
All right. I'm just going to talk a couple bit about things that you guys probably already know about. You're in the high desert. It's not going to be that much different from where you guys are out there in Texas. Same type of outdoor concerns. The guys out there already have been telling us that as they're getting set up, they're seeing lots of fun wildlife out there. They run into a couple snakes, scorpions everywhere, tarantulas, spiders, all the fun stuff. So, your proper gear is going to be important. Long pants, long sleeves, and good sturdy boots out there. If you're not familiar with the mesquite thorns, it's a real thing. If you're wearing tennis shoes, Murphy's Law says that you're going to step on one and it's going to go right through your foot. I was wearing some really decent sturdy boots last year out at Spaceport. I stepped on one and went right through my boot and into the bottom of my foot. Had that thing gone, had I been wearing tennis shoes, it would have been all the way through the top of my foot. So I just give you that story just to, drive home the point that safety is a concern out there. Also, you get really excited and you are, focused on trying to get your rocket and get everything going and you're not thinking about yourself. So make sure you're drinking water, you're bringing your sunscreen, you're doing the basic self-maintenance things so that, you don't end up as a distraction to your team. It's almost inevitable every year somebody's going to end up in the back of the ambulance getting an IV, to rehydrate. So don't let that be you. Make sure you're bringing your water. Make sure you're bringing, hats, sunscreen, sunglasses, protect your eyes. Be thinking about those basic things. Chairs, you're going to need that stuff. So, you guys got a transportation plan? How are you guys going to get down there? I think you said in the report you're going to use a van provided by the university.
Correct. So the current plan is to use a minivan and a truck, both from the university. It's a 14-hour drive from Provo to Pecos, Texas, where our hotel is. So we're going to do a one-day trip, 14 hours straight. Yep.
So check with your university. So some universities do not allow students, for good reason, to travel more than 8 hours in a day. So I would check your university's rules, and then I would caution you. I know it's the old college thing. We're going to strap out drivers. We're going to drive 24 hours. We're going to get down there in one day. Take it easy. You don't need to be in a rush. You've been working on this for 10 months. You don't need to get in an accident or a flat tire on the way down there and miss the event. So,
But
it's the dad in
it's
me coming out.
Yeah, so as far as our university policies, it is 8 hours per driver, but as long as we switch drivers every 8 hours, we're allowed to switch. And we went down to Spaceport last year, which is a 12-hour drive for us in one stint. So we're trying to pull the same thing, but we appreciate the caution.
Yeah. Again, it's the dad in me coming out. Even if you're swapping out drivers, it's not like that second driver is going to be fully rested and ready to go. They've been riding 8 hours already. So, just exercise caution. That's all I ask.
Yep.
All right. And then you've got your hotels. It's going to be a bit of if you're staying in Pecos the whole time, just realize it's like a 2-hour drive between Pecos and Odessa. So, plan for that accordingly, especially those first couple days that you're going to be down there. Unless you're doing like me, you're staying in Odessa the first couple days and then going to Pecos.
So to my knowledge, looking at the maps that IREC provided, that ESRA provided, it was about a 1-hour drive from Pecos
to Odessa.
To Odessa or Midland?
To basically the convention center where it's going to be at.
Okay, that's a 2-hour drive.
Yeah, it's about a 2-hour drive from Pecos to there, and then from Midland to the actual launch site, it's about 2.5-hour drive. It's about 30 minutes from Pecos, from what I understand.
Right. Okay.
So just keep that in mind.
I'll look at that again, because I know I chose a location that I tried to get to like halfway between each, but I might revisit that really quick. But
yeah,
no.
Double check. Maybe my math is off, but that's we were just doing this a couple days ago, and that's what I was seeing.
Okay, cool. I'll keep that in mind.
Yep. You got where you're staying. Just be safe. Are you doing the Airbnb or hotel?
It's a hotel.
Hotel. Okay. Just make sure you're not doing anything like charging energetics or painting in the hotel. Every year somebody does it. So don't let that be you guys. I think that's it. You guys have any final questions for me?
I just checked our hotel to the convention center is 1 hour and 28 minutes, Barry.
Cool.
Okay.
That makes me feel better, because I could have sworn it was like only an hour and a half instead of 2 hours.
Okay. Maybe it's 2 hours from the convention center to the launch site, and then it's 90 minutes to Pecos. Maybe that's what it was.
That makes me feel better. Cool.
Okay. You guys are, I've been working with you since as your reviewer for a long time now. Lots of good back and forth, especially in the beginning in the design phase, and I'm really happy that you guys incorporated my feedback into your design. You've got a solid design, you got a solid team, your rocket looks great. I'm really expecting you guys to do well. So I encourage you, we're near the end. Do the last detailed things to help you earn as many points as you possibly can. So, be ready, have your talking points on point, practice them for when the judges come. poster competition, the whole 9 yards. Just be ready for those things. Those, if you remember, it's long days at the convention center, but when those judges come, it's like, all right, now we got to go. You guys have done a great job. I expect you to do well. So I don't want you to, lose points or drop in the rankings just because of, those final little details at the end. So, great job, guys. Brett, do you have anything to offer the team?
I think you guys are good to go. I'm proud of you.
Yeah.
All right. We're right at about an hour and a half. David, I saw you come up online. You want to offer something?
I just wanted to say thanks to you guys. I know that you're kind of just donating your time here and information and experience really generously. We appreciate both of you, Brian and Brett. It's fantastic to help these young Rocketeers. It's really invaluable. Thanks.
Glad to do it. All right, guys. I'll drop off. We're right about the hour and a half mark, which would
Right.
we plan for. Go ahead.
Thanks, guys.
So, and don't forget, so stop the recording and then submit it. So what I'm going to do right after this is I'm going to submit your final report in the system and mark you guys off so that you're all good to go there, and so they don't bug me or you about the video review. But they're still going to look for it for you giving it to them.
Yep.
I'll send it in, guys.
Okay. So don't worry about it. We'll just have you send it in, Brett.
Don't worry about it. I'll carbon you. I will send it in.
Perfect. Thank you for doing that.
All right. Thanks, guys.